Thank you, Roman. Thank you for being once again one new edition on Reddit, new topic, new subject matter. This is maybe a confusing title. People ask me about the OTAs, OTS, the updates through mobiles in my previous speeches. Please pay attention to the IoT in red. So we are focused on the Internet of the Things, IoT. The reference is to La Cena de los Idiotas, the dinner of the idiots. Their objective was to substitute at least two or three letters to understand what's the topic of this speech. In this movie, some business people look for idiots and invite them to this dinner to laugh at them. So here, certain terms referring to these individuals have to be translated into being invitees into technologies and the wireless devices and technologies. The same applies to it. In the panelists' dinners last night was really the dinner of the idiots, not because of the panelists and speakers, but because of the topics of IoT, the Internet of the Things, and all these devices that are coming in our lives every day. We are taking them at ease because these are supposed to offer us functionalities or novelties, but we should reconsider them from a security viewpoint. The IoT or the Internet of Things or the IoE. The Internet of the Things, the biggest market analysts, the Internet of Things for 2020, we're talking about billions and billions of Internet of Things based and connected devices. In 2014, there were 10 quadrillions of ants. So there will be always American billions, 30 per person. So I'm really surprised about the Wi-Fi alliance. I'm very into Wi-Fi. Uh, they talk about the Internet of Everything, which is a real problem. When I studied the substantives, the nouns, we talk about things, animals, and people. On the Internet of the Things, okay, but the Internet of the Animals, we have farms in New Zealand which monitor cows when they are pregnant. So 10 megs of information per packet in a year. But be ready for the Internet of the Things because it's the third remaining. Regarding certain vulnerabilities, it's a bit sad. It's a bit sad because we have thermostats from several brand news where the interface malware is absolutely vulnerable and they give us access to the credentials of the Wi-Fi organization. The same applies to smart bulbs with this Headmaster thermostat. The protocol, this is smart bulbs created a mesh network, which is set to pound this year, is vulnerable. It's not cipher. They expose themselves, the corporate Wi-Fi credentials or domotics. The same applies to Philips smart bulbs. In the very end, we have a controller we mentioned later that connects with all these devices with which we interact. To wrap up, we are introducing new elements into our infrastructures and networks that open up new doors that were previously inexistent. The latest one is from the Simple Safe alarm. If you get an alarm and you call it Simple Safe, okay, Simple Safe alarm tells you that it's simple in its security and cyber security. It honors its name. So we're focused on communications, this kind of alarm with other devices using the very same modulation and technology they're using. So here you get the references. Just a clarification. When we talk about the Internet of Things, is at a personal level, at the home, at domotics, at the corporate and entrepreneurial thing, is at companies' infrastructures base level. We have sensors all over the areas. At the personal area, we can find the bracelets and the health and sports bracelets you put around your wrist. I didn't know that everybody was ready for the Olympics, and you need to monitor all the aspects and small details in our everyday physical activity. You may not see it with your personal activity. What else? In these situations, many of these applications are for free, so you are the product themselves. So they have ads and commercials. They are integrated with social networks on the cloud and all these marvelous concepts we have been told about. Here, with the entrepreneurial roundtable we had last day, it's impossible. It's good for us to create a hacker bracelet measuring how many scanning commits you do per week. So gauging and measuring the activity. Wow, did you drink up something? How you are pressing on the keyboard a bracelet which are giving you so much information. You can do it with the brainwave system that Alfonso told you. The bracelet can read your brainwaves and they know what you're pressing and touching for sure. That's a good idea for the entrepreneurial people you suggested them. It makes sense. So we can see under the main mobile phones. Are you familiar with this M8? You can see now on screen M8. Are you familiar with this? It's a chip. For what? For what purpose is the chips used?
Es un coprocesador de movimiento que está...
It's a movement coprocessor on Apple. Movement coprocessor on Apple. What is special in it? Do you know what these movement coprocessors have? Compasses, twist logic, a speedometer, accelerometer, and it also has a barometer. The, when you uh, when you when you go up stairs and the calories in the moving up in the altitude, you need to register the barometer. The atmosphere pressure has to be measured. Sexual activity and physical effort are important. If you lost control of all this, and you integrate it with network and you start filtering out information, you may end up suffering with 30 people suffering 30 minutes of moderate effort, or preliminary warming up efforts, and 21 minutes of vigorous effort. And after doing this, they're relaxed 1 hour watching TV, the boy, the girl, and there's 1 hour and a half vigorous effort. So they're doing a lot of sports activity. I would like to be as chef. If I were chef, I would publish on the public networks all their efforts, because I had been for 4 hours and 15 minutes with sexual activity at the top. This could be like a trolling activity. Okay, troll. On this Internet of the Things, what is this? The Internet of the Things, the Internet of the Toys, the Internet of Toys, the Internet of Things. So we have trouble dealing with big tech, with data with the Barbie doll. Being more precise and linking with this may be the Internet of silly people, the Internet of dummies. We don't know where we're moving forward. So when you analyze how you can impact reality with these technologies, I can break down two categories: smart cities and critical infrastructures. Especially smart cities. We had Juanito who presented about this. We have control of air, water, following up with public service, transportation, lighting at streets, parking sensors, and so forth. Regarding personal, corporate, and domestic and areas. We have sensors for everything to activate or deactivate plugs, thermostat, the warming machine, flooding water sensors, drawing up and down blinds, garage doors, gates, pedestrian areas. There is a full range of options that you can monitor with sensors. Demos offer us some harmless devices. I don't want to do it with the whole blind coming up and down. With the plugins, the sockets, the mains, I want agnostic manufacturer because the issues we're going to see are applicable to everybody. The security of the Internet of Things, is really super complicated. So many X needing a protection, but being unprotected, fucking difficult. This is just a little shit. We have a. Wait, please don't applaud me for that. Don't clap me for that. This is fucking shit when it comes to the security of the things. Let's be honest, fucking shit. Shit is cybersecurity. Is now the Internet of Things. We are interacting on a daily basis in a totally unprotected environment. So, if we are focused on the Internet of Things, more technically speaking, we can find magazines about many issues. I can analyze the firmware, and I hope I should not be able to suffer from this because I thought I learned from the past. Of course, no protection anti-exploits, and all. It's very difficult. I can also find services, I cannot call them ancient, are simply legendary. Telnet, FTP, without being cipher is real bad. So, data, sensitive data on the device. If we start moving into the web interfaces, even worse. They're full of things that vulnerabilities, local files, remote problems of authentication, access control. There's only one single vulnerability on the web when we can find real vulnerable things, which is what, which is any volunteer? SQL injection. Why? Because SQL injection has no database. Otherwise, they would be vulnerable as well. Oh, they got it right here. So we start mix this with the fact that from management viewpoint, we use the mobile phone to manage it with all the problems related with mobiles, and all the synchronization and coordination data are on the cloud because nobody wants to open ports in the routers to control to the Internet of the Things. They better connect to the cloud directly. They leave the information there, and you check it out remotely through the browser. It's kind of problematic. And logically, sensitive traffic or not is another issue. Today we're gonna focus on the wireless communications on the devices, which end up talking wirelessly with themselves, with the controller. And I want to open up a new world for you to start research on that because we need researchers on this new area. I take the most of education to give my congratulations to the practical wireless and radio hacking bootcamp we had Tuesday and Wednesday. Oh, many hours with little sleep in a row. And it's a shame that those who wanted to enter this uh, boot round couldn't access it. The kit of tools associated with this course is not viable in the Carrefour next door. We need to obtain these tools from different places, like counseling. So What technology are we talking about? Besides the culprits as usual with Bluetooth cellular Wi-Fi, you told me here about this. I want to go down the world, the, the, under 1 gigs underworld. In this here we can find four ranges of frequencies. It's a non-licensed spectrum as Bluetooth, Wi-Fi, and we have the 300, 400, 800, and 900 megahertz, where we can put the spotlight, 900 in the States and 800 in the European Union. You will find products on both sides. So pay attention to how many technologies are appearing with this Internet of Things. You may be familiar with some of them, and you may be unfamiliar with others. In fact, I didn't know one of them. I met it in it's the CFOX. CFOX for one Internet of Things at cities. You can find them. This is the general architecture you can find on the Internet of Things. So many sensors devices creating a meshed wireless network connected at certain point with a controller, manager, gateway, as you can call it. And this one gives the output onto the internet, and the monitoring window. This connects with traditional database, and with the mobile phone and browser we can access all these devices. This is the main idea. What does it look like? This is it. We are in Kinepolis, in this in the movie cinemas. Of course, we need to refer to them to, of course, to Star Wars. It's trustworthy. What's this? Please. It's not the Star of Death, by the way. A Star Killer! A Star Killer! Says somebody.
Importante. El Star Killer es la nueva estrella de la muerte.
A Star Killer is the new Star of Death with no technologies well evolved. This is your organization, your house, it's our city. Many people have seen the episode 7. How can vulnerate the Star Killer mechanisms to sneak in? Because we came here to talk about security and cybersecurity. What do they do? As Roman says, it could be dated back to 18 years ago. We're used to it. What happens here? With the Millennium Falcon goes in, and how they attack the Millennium Falcon, how they can get arguing with this. We cannot hear this person speaking with that microphone. Eric got it. I make sure that if this is not well prepared, I'm sure it is not prepared at all. I swear to God, he got it right. In the name of Star Killer, that's what's happened. It happens as follows. They go at the light speed, so they can trespass the shield in the blindage, and this is happening. How many of you have a wireless IBS? Very few of you. Let's guess you get it. What is going on here? How many starting using 800 to 11 AC in your IDS details? 812 point. Okay, Star Killer detects that somebody is sneaking in at the light speed, because the light speed, when we are mixing up matter and energy, it means you go quickly at the bigger frequency. New technologies going at a different frequency, or much more frequency, are sneaking in without knowing them. So it's the very same comparison. So you remember, in 2013, I introduced you iStupid, indiscrete SID tool for the unknown PNL on iOS. Today I will introduce you with Idiots. Idiots are on the Internet of Things is a tool to interact in detecting Internet of the Things assets. Interact to detect Internet of Things assets. IDOTS is able to identify and detect have new devices on unexpected frequencies and interacting with them. What can we do? By the way, when you start looking for it, you can find so many idiot quotations or talking about quotation. I leave you for your discussion. So can you remember this movie? Their idea was to locate and convince idiots to invite them for dinner. We will try with this techniques. I want to get focused on the tool. I want to focus on the techniques. Can we do inverse engineering about this with our current activities to detect these new components using new frequencies and know what is happening around me in my environment? What am I confronting? What other technologies can be manipulated by somebody on the Internet of Things? To be specific, under one gigahertz range. The part the finding remarks might speak would be about a demo. Let's cross fingers the demo will be working at the end of my speech. So hackers attending my course, no, they did drawings in radio frequency, but I hope it won't happen. You can play around outside. I'm not kidding. Let's focus on these devices. I took this because I'm a kind of agnostic in brand new names. This is a big problem and it's generalized. Is this funny one. This device has two channels, one and two, and the possibility of two states, one and off, and four codes to control different devices. We'll do so with plugs, mains. This will be the entry door, a thermostat control, a blind. All devices are using a similar technology. So let's try to move forward and move into the other screen. Can you sit properly? Can you adjust the slide? Oh, now it's perfect. Only 2 millimeters on the right. So let's play around with all of this. Before anything, I want to show you. I want to show you what we can see from here. You are there at the back, and we got here an element which is the jack tested one. This is not an SDR device. It's a wireless IC transceiver. Receive and transmit is wireless and is an integrated circuit to work with certain technologies. Here we can find the famous Kai secret is the SDR in essence, which allows you to play around at a software level with the signals we're receiving, and then we can integrate them with the other device. Very first attack we can suffer. Let's firstly have a look at the radio frequency. I won't take out any waterfall, so don't take pictures, so we don't have any trouble with the frequency. I have FFT with the frequency graph for you to check it out. This is using the Osmo Spectrum browser. We can see a more stabilized signal when I press the original controller. One light turns on, and when I switch off, it turns off. You see that the green peak with the signal we are transmitting and receiving, everything is working as expected. Here is transmitted on the frequency 433.79 megahertz. Perfect. The very first attack we can conduct against these environments, this is okay. This is the scripty attack. I will try to capture this signal. I don't know how is module inside. I don't know anything about this signal, but I can transmit it, and something will act in relation to this signal with minus R of receive on hacker expert transfer, we can receive the signal, and then we can transmit it. It's funny. The hacker effort is in normal state. Is You need to be very careful about the signal because there may be background noise and this can affect the transmission. So let's analyze the behavior. I will start capturing. I will activate and stop the capture, and this is it. Am I supposed to have captured the signal on this file? It's a capture file, C file. I turn off the light to have it turn off, and I will try to retransmit it. The remote control is there. If I change T C file is changed to T Chaleon C file. Let's see if it's turned on again. We may not have it turned on now because the signal capture has background noise. It's not high quality, unfortunately. So I want to increase the gains of the signals, and I didn't capture with bad quality. Let's see if it's working. In this very case, it doesn't work. Let's try it again. You can see it has traveled. So let's go at the speed velocity transmission. I also have the microphone. There are some distorting elements that can affect this range. So let's try finally, because due to the environment, it's not okay with the signal. No results. I didn't get it, even though I pressed replay because the captured signal has not enough quality for us. This is okay because Squid TV only captures and retransmit, have it more difficult. I can try it again, but let's move on to more interesting topics. We should approach the transmitter to the receiver much better to having obtained a better quality. Perfect. So far so good. So let's try doing this. Let's capture this signal as we seen before with the Osmocom. Let's have a look at it. Now I take the remote control once again, not to enlarge it too much in the snapshots in the capture. I record it, I generate the signal, I stop the recording, and I analyze the recording. I press, I send the signal, stop, and this guy is activated. So we got a recording we can analyze properly. We firstly analyze it with another tool to have a look at it. This is kept by default on TBP. So I copy it. I copy CP, copy TM, name. This is C file to FFT.C file, and this is the file I'm getting.
And we open it up. In the tools, the only thing I have to be careful with is saying that this is the sampling rate that I've used, and this is the frequency of the capture. There must be a match between the different tools, okay? So let's see this with in Spectrum, which is this tool. It allows us to see a waterfall in static. This line is for my receptor. If we go down, at a certain point in time, we'll see something like this. We've captured the signal, okay? You see this, which is what the remote is transmitting and what the receptor is getting. What is striking here? What happens in those gaps that we see there? What does it look like? What did you say over there? They are repeated over and over again. It's the same signal. If I show you two, and you try to spot the differences, there's none. They're the same. Because of the devices and the type of modulation, they send the same signal once, then twice, 3 times, or 5 times, whatever. But it's the same signal over and over again. Let's play around with this. Let's take this signal. Let's increase the size. Perhaps not so much. Here we have increased it in the horizontal plane, the frequencies. The signal is clearly focused on a certain frequency. There's only one frequency. So we're beginning to feel what type of modulation is being used. It seems like this is amplitude shifting, we're modulating the zeros and the ones depending on the amplitude and not depending on the frequency, which would be a frequency shift key. So we zoom in to take a closer look, as you see here. Let us take one of these and let us play around with the power so that we can keep things under control. To take a look. So we zoom in. Are you beginning to see what we have here? How about that? It seems we have like two types of lines. One is short, the other one is longer. It's like different pulses, if you like. If we get closer, let me do something. I'll play around with this. This is much better now. So I'll go right to the start of these signals. Any of these. Here we have a gap. So we see a pulse. It would be a bit to 1. Then if we measure the space in this transmission in time, I would see that there's something like 1, 2, and 3 units at 0, and then I could count bits, like 1, 0, 1, 0, to do reverse engineering for this. Let's try and do it quickly for this example. Thank you, Roman. So we have ones and zeros, and then it would be interesting to see. I'm going to increase this that way. How about the size of any of those transmissions? We'll see this later in greater detail. We want to see how many milliseconds. These are milliseconds or microseconds. Take a look here. 3, 2, 1. And a little bit more. It's just above 30 microseconds or 0.3 milliseconds approximately per unit of time, 0.33 or something like that. So let me increase this slightly, not that much, so that we can take a look at this and count. If we have 1000 in hexadecimal, what is 1000? 8. And 1110, we almost got to the F with the last one, that's E. Okay? So let me do something. I'll get this way, so you see this can be done manually. I'll start counting. I'll increase here. Right, there it goes. That's a bit better now. I'm going to move it to the left, and then we start counting. The first one is short and then long, so that's an 8. How many 8s do I have? 3, 4, 5. 5 8s. And now I have an E, yeah? 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. And then we have a long pulse, which is like having 3 1s and 1 0. That would be the E. So we have an E. That would be an 8. That would be an E. An 8. An 8. This one here. Another 8. Another 8. Another 8. An E. An 8. An E. An 8. An 8. Another 8 here. Another E down here. Another 8. An E. An 8. An E. And an 8. Right. If I counted correctly in my process, you see that this is an even number. Sorry, an odd number of characters. So I add a 0 at the end, which is that blank gap and not transmitting anything. So I would have characterized the first channel. Remember, we have a device that has 2 channels, 1 and 2, 4 codes, A, B, C, and D, and on and off. That means it has 16 possibilities. That's why we have the chart here. 16 potential combinations. But we've selected the first one to see what we can do with it. Okay. So this I'll save, and then we'll try and use it. So before I move on to that part, it would be interesting for you to know GNU radio. GNU radio, and to be more specific, GNU Radio Companion, is the radio defined by software that can allow us to create our own applications, our own software applications to manage signals. So let's do our best, trying to come up with a scheme, a software scheme. If we have time later, we'll play around with it. So let's start with a flow graph, a simple flow graph. Here we create a variable where we can input the frequency. I know that the frequency I'm working at is 433.9, for example. Raised to the power of 6 megahertz. The first thing I'll do now is to include an element that can capture the signal. In order to do that, I'll go and search for Osmocom source. This is a component that shows the input and will send the signal to a GUI. Which one? FFT, because it is similar to what we saw before. And now we're going to send the data over to that GUI. And we will also go into a file sync. In GNU Radio, sources are these, and sinks are the destinations, okay? Where the signals end up at the end. Right. In the file sync, we'll say what file to use. We can call it grc.c file. Okay, the little file where we store the signal. Okay. With that, we should have that ready. And now we ensure that this guy will show us in the chart the frequency that we're actually using. So we go for, right, that's baseband frequency. We say is the FREQ variable that we created before. For the source, we say what the frequency should be, FREQ in this case. The sample rate will change now, at the speed of sampling. And then in HackRF, we would like to start with a hardware gain for the front end, which is disabled. Quite likely we will have enough of the signal as it is. And then in terms of the sample rate, we can start capturing something which is not too powerful. So 2 million samples per second. HackRF can go up to 20 million samples per second. Okay, so that we've got enough. So with that, what do we have? Those of you who have never seen GNU radio, we are capturing signals with a ratio of 2 million per second, 2 million samples per second, at the frequency I'm interested in, because I've identified it previously, with the normal setup, with no extra gain at the start for HackRF. I'll have a chart and I'll be capturing it into a file. Okay? So what I'm doing here, because in the chart we will not see too much. As soon as I launch it, as soon as I generate the signal, I'll stop it. Okay? I'll stop it so that it doesn't capture a file which is too big with too much noise, and then we'll play around with the signal. Right. So let's launch it. Well, the first thing is to save a flow graph to a file. We'll call it rooted 2016, rootedcon 2016. We're in the demo directory, so we launch it. We see it launches the signal, we generate the signal, and we stop it. I've done it quickly so that we can ensure that the file that we have generated, sorry, that wasn't the thing, we had it over here. This little file called grc.c file is 57 megabytes. Bear in mind that it's sampling, that it's taking samples at 2 million per second, so it's capturing a lot of traffic, a lot of information. So now we are done with our file. We will be interested in analyzing this using GNU Radio. We will not do this because of time limitations, but we could do it. We now invert the source and the target. We say that the source is a file, The destination is a device, and I would send the file. But instead of doing that, let us convert the chart somewhat to do the other way around, reading from the file, analyzing it. So let's get rid of those links. We could create a new project, but we'll first move these guys. I'll leave the chart as it is. We now have a file source, which is the one that will read from the file that was stored beforehand, grc.c file. What we now have to take into account is, as soon as we are reading from the file, my computer is going to be moving really fast. So we'll use a throttle to slow it down. So send the input here. The throttle is at 2 million samples per second. And the last thing we would be interested in would be a little chart, WX, to see the scope. The scope sync is not like the FFT, it's like an oscilloscope, okay? We'll see the signal as if we were using an oscilloscope. That will be connected here, sorry, no, we'll get rid of that one. We'll connect that here to see the signal before we process it, and then we'll process it, thank you, we'll process it with the next module. Let me tell you about it. Complex to mag will allow us to take the complex numbers that are being captured by the HRF and change them in terms of the magnitude. I connect this and that this way. You see that data types are failing. I say that they're now handling float type of variables. So what do we have now? This is very simple. We're reading from a file source. This is the origin. We apply a limit to the speed because it will be the CPU at 100% otherwise. Then we'll see graphically the same chart we had before, and we'll pass it through a module. We don't have time to explain it. The module simplifies the signal so that we can take a look at those figures or captures so that we can interpret them more easily. If everything goes well, you see that the file is being repeated all the time so that we can see the signal and analyze it. So let's move forward. It's complaining because these two are not linked, so I disable them. There's nothing in red. I launch it, and you see that at the bottom we see the signal. You see the peak. Well, the problem is that there was quite a lot of noise. A lot of signals were generated. We're not talking top quality. Okay, well, let's take a look. Let's see how much noise. What am I doing in the oscilloscope? You're only seeing noise. I'm going out, I'm zooming out now. There's too much noise. I'll make it smaller. And I'll minimize that noise. There we have that noise, and we see the signal. You see the signal? There it goes. We see the pulses that we were seeing before with the other format. If I extend this a little bit, if the interface allows me, and I try to stop it quickly, what I would like you to see, there it goes, is that we can analyze the pulses in the signal that we were seeing before. You see the small pulses and the long pulses. That's 1, 0, 0, 0, or 1, 1, 1, 0. Therefore, we could take the signal and analyze it. Here, it might be easier to take a look. Let me reduce this a little bit. Perhaps it would be easier to take a look at that, the thickness of those pulses. You see that we're talking of milliseconds here. So if we do the calculations, it would be 0.30 that we saw before. With this, I'm trying to show you that we have different tools that will allow us to do this analysis. It doesn't let me now, but okay, there we stopped it. It's more clear now. Right. So far, the only thing we've done is to interpret the signal, store it, and then send it again. What happens if instead of that, what we do is to try and interpret the signal and see how it works? In order to do that, we're going to move over to the other device, the one I mentioned before. This device allows me to do the following. Once I know the frequency and the sample rate, and how much it costs me to send a pulse or to send a signal, start using it right away. That's the goal here. In order to do this, haven't seen anything here, right? We do a clear. I launch RFCAT, which is the tool interacting with this guy, with this device. It is the best thing ever since frequency hopping, and you'll see it in a minute. What can we do here? Now we say that we want to interact with this device to see if we're able to work on that signal by doing reverse engineering on the signal to rebroadcast it and have the correct type of signal. D accounts for the dongle. This is a USB device. So D dot set frequency for the operating frequency, which is around 433. 433.90.80. It was 433.78, something like that, in hertz. That would be the frequency in hertz. And now we have to tell it the type of about the type of modulation. You saw about the type of modulation in GNU radio, the peaks we had. Sorry, I closed it. But anyway, the peaks went from amplitude 0 to a certain amplitude, and then they went down again. That modulation is called on-off keying. Okay, we go up and down with the signal regarding the reference amplitude, and that's what lots of devices use, like the alarm that we saw earlier. So we tell the modem, we say set modem for a certain modulation, and we'll tell it that the modulation we have for all the ones compatible with this device is ASK in amplitude, OOK, right, on-off keying, right. The only thing left now is to tell it the rate at which pulses are being sent, so that we know what units of time we're dealing with. We just tell it set modem data rate. This is Python, so we tell it to calculate an integer between 1 and what we saw for those impulses. So 30 to 33 microseconds. We go into milliseconds here, 1, 2, 3, and that's 33, okay? It will calculate the baud rate. Right, I missed the comma there. This is 0 point. Okay, two float variables generating an integer. If this goes well, I'll try to transmit and see what I can get. So I say RFX mit, and then I tell it what to transmit. In order to do the transmission, remember we had captured at the beginning that pattern we had here. Remember those A's and those E's? Right, so assuming we've done it correctly, and we'll see it in a minute, let's go into it. If we go into transmission, we simply have to send it in hexadecimal format. So will you please transmit this pattern that we have sent? Please encode it in hexadecimal so that it uses slash x value, and we send it. So let's try this way. It will probably not go on. Okay, that's this guy transmitting. So it sent it, but it didn't go on. Why? How many times did I send it? Once. We've seen that because of tolerance, it sends it more than once. So we could tell it to send it 10 times. It doesn't go on. A common reason for this is that we need some more padding, some more zeros, so that there is enough distance. Remember, those were black gaps between the signals. So the simplest thing to do here is to take this and add, I don't know, 2, 4, 6 zeros over here. We tell it to decode in hexadecimal. This part as well, sorry, in hex over here. And if I'm okay with the brackets, which I think I am, we run it, and it doesn't go on. Okay, let me just take a look at this.
Ah, sí, cierto, exacto. Eso es lo que estoy haciendo, que estoy...
It's true, I'm multiplying here in Python, only this last part of the padding. That is not what I want. What I want is to send the full signal 10 times. And there you are. The light is on. Good. What can we do now? I said that there were a lot of different codes. So we would need to do additional reverse engineering to see what happens when we pay, what happens when we change the channel, what happens when we have different values. We can do this as follows. Let us assume that we have that frequency, that modulation, and that transmission rate. And now I just have to start the capture. We're running out of time, so let me just try and optimize this. If I now do another listen to the signal, I will see what happens with this guy. I would press the button and I would capture nothing. You see, I'm capturing nothing. The reason for that is that we've seen that the signal had no preamble, okay? Usually, wireless signals have preambles of zeros and ones to synchronize the clock and things like that. But we didn't have that part, so we need to go into low-level values to fine-tune it. We would basically tell it to deactivate the preamble. Okay, preamble quality threshold. A range we're not interested in. We can disable the preamble completely. We can tell the modem that we don't want to use any preamble at all, because we've seen that there is none for this signal, 0. We could also say, just like a start of traffic, my traffic always starts with an 8. If we had taken more samples, we would have seen that it's always an 8 at the beginning. So it would be interesting. So that you know this is my signal. Take a look at signal starting with an 8. So the sync word starts with something similar to 0x0008. If you recall, when I showed you this started with an 8. If we had taken more samples and we had done more reverse engineering, you would have seen that all of them start with an 8, which is a good reference. And now I could ask it to listen. If I now listen and I send the signal, we're still not getting anything. If I don't forget anything, we need to go into the sync mode. In the sync mode, don't be too strict, and let me discard those which don't have all the exact bytes that I told you about. So let's try to listen now. We'll launch it. Doesn't capture. It should be capturing now. This is demo effect now, because it's activating this one. I probably overlooked something because it is not capturing as expected. Okay, let me just check it up. We have everything correct. We have no preamble. We have disabled the quality threshold. And certainly there should be data there that we should be able to capture. The rate is correct, and the modulation and the other things seem correct. So let's go again. But there's something there. There's a parameter somewhere that I overlooked that is not capturing. Right. Okay, what I wanted you to see is that we start getting a signal, or signals, but it would be a signal mixed up with trash. The next step down the line would be to determine the length of that signal. If you recall from the previous analysis, it was 26 hexadecimal positions. That's 13 bytes. So we would tell it that the size is 13 bytes. What is the beauty of this mechanism without FCAT and Python and all of these capacities? Well, we can put this into a Python file and do it in an automated manner. In this case, I've created a little file myself called HomeKit. If you take a look at the transmission part, this is what we saw before. How I send the signal by simply identifying in what specific values, it changes the code, it changes the channel, or goes into on-off, activation, deactivation. That's the idea. And when capturing, I'm doing what I did now. We've changed the frequency, the modulation, and the rate with the values that we have applied for the capture, telling it that the size of the packages is 13. If everything goes well, since there's a typo somewhere in the console, but the script should be okay, I'm going to load the script. This is a Python script. We load it up, and now all the functions will be made available. If I make a call to this function, RX HomeKit, and I pass the dongle to it, it would start listening. As soon as I press, it would capture traffic. I'm not only capturing the raw traffic, but because I've told it what values I'm expecting, it tells me about the channel, the code, whether it's on, whether it's off. So it decodes everything because it understands the protocol. In fact, let me show it to you. Here in the capture area, this is the smart one. Let's get rid of this print command, this hash. I load the file again. We launch the capture procedure again, and you see the 8 E's we saw before. Take a look at on and off. What happens between them? Let me find it. Okay. In on, this is an E. With off, this is an 8. And the same goes for positions of channels. Since we've done reverse engineering, we know how the system works. 1. Remember that this is interaction and detection. Okay, we have the detection part. We now know when someone presses a button, there is a certain frequency for this period. If they're sending it, we know whether it's an on or an off, whether it's channel 1 or this will be the D channel. The D area is detection. And then it's interaction. That interaction we've seen before. We've transmitted it and it was sent. In the script, you've seen that this is very simple. Here, I have just created ABCD 1 and 2, on, off, and I tell it to change the values. Remember, we've seen that 8 or E was on or off in the final part. Well, there it goes in the sequence. And that can be part of a function that lets you transmit whatever you want. I can come here and I can tell it to do a TX HomeKit. I never remember where. I do help for that. So I do TX HomeKit, use the dongle, and make sure we're activating 1 in channel A, and I want to deactivate it. And this light goes off. Okay?
Que llamar para controlar todos los distintos cacharros. Y entonces aquí es donde ya, digamos, damos el paso
Here we can give the extra step into doing the totally idiot Internet of Things. Here we use another frequency which has been analyzed as well. Let's load this idiot script, which is idiot with dongle, and it implies sequences of events. Let's try, let's cross our fingers, let's see what happens. Lucky one. So far so good, this is ready. We have spent our time in cybersecurity. We need to exemplify. You put it into doubt. Of course, I didn't have another password. I would take just the one hacker DF. I do the reverse engineering for these protocols, and I put it on this drone we can see around these days. So the thing is super serious. Here we can play around with these Internet of Things under 1 gig frequencies, 1 gigahertz frequency. If I put it on a drone like it's like the Millennium Falcon, this should be super good. Star Killer before the speed light, light speed. Wow, take into account how final remarks and recommendations in 2015 I started using the Spanish probers. Spanish probers apply here very well. When the technologies of your neighbor start risking or failing, you have to update everything. This year, I'm bringing over another program, refrain. You should be applied with Spanish refrain. Bit flying into the pen, which is what we're doing right here. Besides, if it's the frying pan or the melting pot is super intelligent with Bluetooth Smart to connect from the iPad to machine at very low cost on the Amazon storehouse. Wireless technologies in the pressure cooking melting pot. So this is the credits for having me supported and tolerated with me over my past researches. Recommendations, please take into account the importance of raising awareness about these problems for the manufacturers and ourselves to encompass all these devices and technologies into high quality cybersecurity levels. A bit of ciphering, integrity authorization, otherwise it would be too late. So all these devices are coming into our lives, are integrated, and you can see how things are working so bad. Thank you very much. Thank you. Questions, please. Two questions. Okay, who is that the bread guy who can ask first? Didn't you understand anything? I did so bad. There are no questions at all. A solution could be to have jamming house-made devices with white or noise generators to protect my house. Difficult to find a solution with the flatten antennas from your walls outside to stop jamming yourself. In this case, the garage won't open yourself, and the bird door won't be closed if it's at the same frequency. The blinds with reflections. What can we do? All these frequencies have to be used with protocols which are different of. I'm sending you the signaling, authentication, ciphering, more expensive products, but we need these capacities. One question over there. Congratulations for your nice talk. What do you think about the threat protocol presented with Cisco? In principle, with security as the main objective, cybersecurity as main protocol, PRE protocol. I don't know this protocol into detail. I haven't taken out certain protocols used by Nest and similar solutions in controller, as a ZigBee, ZetaWeb, and so on and so on. Which is the most important problem. It's true that these protocols are coming with certain cybersecurity in the specifications of the design, but we know how this world works. Bluetooth and Wi-Fi came with embedded cybersecurity in the design, but we had some trouble. The protocol design does not oblige you to death to be used in all capacities in cybersecurity, so some manufacturers won't implement it, others will. And by seeing how manufacturers implement cybersecurity going this way, for us to, people like this, to audit this cybersecurity and try, there have vulnerabilities. All these protocols try to add up more cybersecurity. All this, I'm not talking about the future. I'm talking about the present, something which is coming in big waves to us. Who has audited all these protocols? Who has audited all these implementations? Little, no, very few people audited. So let's take it for serious. I have to cut down on questions because we are running out of time. Thank you, Raul, for your presentation.